Alright, before we develop matrix theory any further, let's do some example problems. So I'm given matrix A and B. Let's solve a little matrix equation. Let's find matrix F if 3 by x minus 2 times the matrix A is equal to A plus 4 times the matrix B. The cool thing about matrices and matrix equations is that we can, for the most part, use the principles of algebra. So my goal would be to get 3x on its own, or just x on its own, because it is the unknown that we want to solve for, and have all the known quantities on the other side of the equation. And I can do that by first adding 2a to both sides of the equation. So the 3x remains minus 2a, and let's add 2 times the matrix A to the right-hand side, to the left-hand side of the equation. And what I do to the left-hand side, I have to do to the right-hand side as well. So this means I have to add 2a, 2 times the matrix A to the right-hand side. Alright, so we have minus 2a plus a 2a, and these would add each other to become the 0 matrix, because these are additive inverses. So that leaves us with 3 times the matrix X plus the 0 matrix equals, on this side we have scalar addition, so we have 1 times the matrix A plus 2 times the matrix A plus 4 times the matrix B. So then on the next line, 3 times the matrix X plus the 0 matrix. Well, the 0 matrix is the additive identity. So anything plus the 0 matrix is equal to itself. So we're left with simply 3x on its own. On the left-hand side, 1 plus 2 is equal to 3. So we have 3 times the matrix A plus 4 times the matrix B on the right-hand side. Okay, let's multiply the left-hand side by 1/3. And if I multiply the left-hand side by 1/3, I have to multiply the right-hand side by 1/3 as well. So now we can use the law of distribution. So we know that scalar multiplication is distributive for matrix addition. So on the right, we can distribute the 1/3 scalar multiplier into both of the terms. So we have 1/3 times the matrix 3a plus 1/3 times the matrix 4b. Now we also know that we can multiply the scalars together before we multiply them into the matrix through the law of associativity. So 1/3 by 3 gives simply 1. So we have 1 times the matrix X, or 1 times the matrix X is just the matrix X. And similarly on the right hand side, 1/3 by 3 will give us 1 times the matrix A, and 1/3 by 4 will give us 4/3 times the matrix B. So the matrix A is equal to 4, 1, 7 for the top row, and 2, 0, 5 for the bottom row, plus 4/3 times the matrix B, which equals 0, 6, 5 for the top row, and 3, 3, 8 for the bottom row. So let's scalar multiply matrix B first. So we have 4/3 times 0 equals 0. 6 times 4/3 is equal to 8. 4/3 times 5 is equal to 20 over 3. 4/3 times 3 is equal to 4. 4/3 times 3 equals 4 again. And 4/3 times 8 is equal to 32 over 3. So we copy down the matrix A. And to finish, we simply then add the two matrices. So 4 plus 0 equals 4. 1 plus 8 is equal to 9. 7 plus 20 over 3 is equal to 41 over 3, 2 plus 4 is equal to 6, 0 plus 4 is equal to 4, and 5 plus 32 over 3 is equal to 47 over 3. So we'll simplify these two fractions a little bit, make them into mixed numbers. 4964 remain, and 41 over 3 we can write as 13 2/3, and 47 over 3 we can write as 15 2/3. Okay, for example 2, let's find the product of these two matrices. So the first entry is the product of the top row of the first matrix by the column of the second matrix. And when you come to learn about vectors, we're actually finding the dot product of this particular row 3, 0 and the column 5, 0. So 3 times 5 plus 0 times 0. So the next element is the dot product of the top row of the first matrix and the second column of the second matrix. So we have 3 times -1 plus 0 times -3. So for the second row we have the product of the second row of the first matrix and the first column of the second matrix. So 2 times 5 plus 4 times 0. And finally we have the product, the dot product of the second row of the first matrix and the second column of the second matrix. So 2 times -1 plus 4 times -3. So evaluating these expressions, 3 times 5 plus 0 is equal to 15. 3 times -1 plus 0 is -3. 2 times 5 plus 0 is equal to 10. 2 times -1 is equal to -2. 4 times -3 is equal to -12. So -2 minus 12 is equal to -14. Alright, let's do one more example to wrap up this video. Let's find the product between these two matrices. Now before we start, we need to check if multiplication is defined for these two matrices. So we have a 1 by 2 matrix and a 2 by 3 matrix, 2 rows and 3 columns. So are these matrices conformable? And the answer is yes, because we have the same number of columns in the first matrix as rows in the second matrix. So these will cancel and we should end up with a 1 by 3 matrix when we find the product. So the process is the same before, row by column. So 3 times 2 plus -5 times 4. Again, row by column. 3 times -3 plus -5 times -4. And once again, row by column. 3 times 1 plus -5 times 0. So here we have 6 plus -20, which will be -14, -9 plus +20, which equals 11, 3 plus 0, which equals 3. So is it possible to multiply if these matrices were switched around? No, because we have 2 by 3 here and 1 by 2 here. So no equal columns as the number of rows. So multiplication would not be defined if we had switched these matrices around. Alright, so let's wrap up this video. If you have found it useful in your studies, please like, share and subscribe. And it takes me a lot of time and dedication to produce these videos, so I would really appreciate it if you can help me by making a small donation, and that way it will give me the resources to produce more videos to help more math students in the world. Thank you so much for watching, and I'll see you on the next video.